Hey, fourth year, and welcome to this revision video based on nuclear chemistry. Again, not the biggest topic, but there's quite a bit of understanding for this topic. So I will go through it as slowly as I can, and hopefully this will help. Okay, so we need to know that radiation is essentially the changes in the nuclei of an atom. Unstable nuclei, called radioisotopes, can become more stable by giving out these types of radiation. So essentially what happens is sometimes the nucleus is too big, or for various really complicated reasons that you don't need to know, the nucleus of the atom is really unstable. So in order to stabilize itself, it kicks some stuff out. And that can be an alpha, beta, or gamma radiation. Okay. Alpha consists of 2 protons and 2 neutrons and have a 2 positive charge. They are considered a helium nucleus because helium has 2 protons. They have a range of a few centimeters in air and are stopped by a piece of paper. They will be attracted to a negatively charged plate. Okay, that's because they're positive. Negative charges will attract it. Okay, so need to remember alpha nucleus, 2 protons, 2 neutrons, have a 2 positive charge. They can get stopped by a few centimeters of air or a bit of paper, and they'll be attracted to a negatively charged plate. Beta particles are electrons. Simple as that. That's all a beta particle is an electron. They can travel over a meter in the air, but are stopped by a thin sheet of aluminium, and they will be attracted to a positively charged plate. That's because we know that electrons are negatively charged. Remember, opposites of charge or attract. Gamma rays are essentially electromagnetic waves, so it's the same type of wave as light, infrared. Okay, it's really highly energetic. They are the waves that are emitted from the nucleus of an atom, normally because the atom has rearranged itself in some way rather than kicked out a particle, and that rearrangement releases energy, and the energy comes in gamma rays. They can travel really far, but can be stopped by barriers made of lead or concrete, and they are not deflected by an electric field. Because they're not a particle, they don't have a charge, they're not going to get attracted to either positive or negative. Okay. If we're looking at nuclear equations, the alpha particle is a 4-2 helium. Okay. Nuclide notation, that's the word I was looking for. The nuclide notation for an alpha particle is 4-2 helium. A beta particle is 0, -1e. Remember, this one gets slightly complicated because at the bottom is the atomic number, which is normally the number of protons, but electrons kind of have a negative charge. So we put a -1 down there, which is the only time you'll see a negative number in a nuclide notation. Proton is 1,1p, and a neutron is 10n. Okay, most of the time you won't need to remember what a neutron is or a proton. They will give you it in the equation, but it's useful just to keep in mind so that you understand how to do a nuclear equation slightly more. Okay, these are examples of nuclear equations. What you need to remember for these is that the numbers on each side need to add up. So on this side we've got 2, 5, 6. That gives out a helium nucleus or an alpha particle with 4 mass. So therefore we are left with 252. 256 before the arrow, 252 plus 4 gives 256 after the arrow. And that's the same for no matter what. Okay, you need to make sure that your numbers add up before and after. So for this example, sodium, it's going to give out an electron to form magnesium. It's 24 mass before, and an electron doesn't have any mass, so it's still got 24 mass. However, it has 11 before. It's given out an electron, which we can think in our head as -1. Therefore, it's gained a proton, so it becomes 12. It's 11 before. 12 take away 1 gives you 11 as well. Okay, so the sum of the atomic numbers on the left-hand side is equal to the sum of the atomic numbers on the right-hand side. The same is true for mass numbers. If you keep that in your head, nuclear equations won't be difficult. Okay, remember that sometimes you'll have to work out what is left over afterwards. If there is a new atomic number, it will be a new element. So sometimes you'll have to look up your periodic table. Right, okay, this atomic number is 101. What is 101? It's MD. Mind has gone blank. Cannot remember what MD is right now, but you know what I mean. Uses of isotope. Radioisotopes have a range of uses in medicine and industry, and uses are linked to half-life and or properties of the radioisotope. So sometimes you'll get a question asking you to comment on the suitability of a radioisotope. Normally, it would be something like, why isn't the half-life of this substance is 7 hours? Why would this not be a good radioisotope to use in a smoke detector? Well, because the half-life is only 7 hours, you would have to replace that smoke detector every 7 hours rather than every like 30 years. It could be this radioisotope gives out beta particles. Why is this not a good radioisotope to use in smoke detectors? Well, because beta particles wouldn't get stopped by smoke, which is what you're trying to detect, etc., etc. Always think, is the half-life, is this going to last a decent amount of time? And can the radioisotope penetrate or get stopped by whatever you're trying to test for? Okay. Talking of half-life, half-life is the time taken for half the nuclei of a particular radioisotope to decay. Half-life is the same. So for carbon-14, the half-life will always be 57,000 years. I had to think there. Okay, you don't need to know that. I'm just sad and do know that. Half-life of that carbon radioisotope will never change. It doesn't matter if it's at freezing temperature or if it's at boiling, if it's at like 1,000 degrees temperature. Okay, it will always be the same. Okay, it's unaffected by chemical or physical conditions. That's why it's a really good way of dating something. Carbon-14 is used to date samples of old of fossils and things like that, because we can accurately measure the amount of carbon-14 that's left and use that to date how long something is, because we know that the half-life is always going to be the same. Okay. The half-life calculations aren't that difficult, but they are easy to get confused as to what to do. So half of the time you will be asked to work out the half-life of something. Okay. And you'll be asked, it's falling from 1.6 to 0.1 in 2 hours. What is the half-life? The key to this part is remembering that the arrows is the number of half-lives, not the number of numbers. So however many arrows you write down is the number of half-lives. 1.6 decays to 0.8, to 0.4, to 0.2, to 0.1. There are 4 half-lives because there are 4 arrows. 4 half-lives is 2 hours because this total time is 2 hours. 1 half-life is half an hour. Okay. Sometimes you will be asked to work out how much will be left over. So a radioisotope of phosphorus has a mass of 80 grams and a half-life of 14 days. Calculate the mass left after 56 days. The first thing is to work out is how many half-lives is that. If one half-life is 14 days, you can divide the total time by the half-life to give you the number of half-lives. Okay. Now that you know the number of half-lives, start at 80 and half it 4 times. Remember that arrows is the number of half-lives. It halves once to 40, twice to 20, 3 times to 10, 4 times to 5 grams, and 5 grams is left. Okay. Sometimes it will ask you for a fraction. If it's asking you for what fraction will be left at the end, start with 1. After 1 half-life, it goes to a half. After 2, it goes to a fourth. After 3, it goes to an eighth. After 4, it goes to a 16th. Okay. You can do the same for percentages. Start at 100%, 50%, 25%, 12.5%, 6.25%. Okay. And that is everything you need to know for nuclear chemistry. So feel free to go ahead and do the work for today. If you need any help, please comment on the Teams post and one of us will get back to you as soon as we can. Okay. See you again. Bye.